Chapter 3, Polynomial and Rational Functions, Section 3.6, Rational Functions. We'll now conclude Chapter 3 with a study of an important class of functions called rational functions that are related to polynomial functions but really have to be considered separately since it's really a separate class with its own properties and characteristics. Recall that a rational number is just the ratio of two integers, which we'll call n and d for numerator and denominator, where d, that is the denominator, is not equal to 0. In other words, a rational number is a number of the form n over d. So basically a fraction consisting of two integers. In a similar manner, a rational function is the ratio of two polynomials. So the precise definition is that a function f of the form f of x equals n of x over d of x, where n of x and d of x are polynomials, again thinking of n as numerator and d as denominator, f is called a rational function. The domain of f is the set of all real numbers x such that the denominator is not equal to 0. Now with polynomial functions, we had an unrestricted domain. The domain was the set of all real numbers unless we restricted it ourselves. With rational functions, we have to pay attention to the possibility of division by 0. And this is one of the things that distinguishes dealing with rational functions from dealing with polynomial functions, is the fact that we have domain restrictions and we have to understand what happens in cases where the function is undefined. We actually have already encountered some rational functions back in Chapter 2. Two of the basic functions in our list from Chapter 2 were rational functions. We had this set of basic or elementary functions that we used, especially when we were dealing with transformations of functions. And these are two that appeared in the list. They are the reciprocal function f of x equals 1 over x and the reciprocal square function f of x equals 1 over x squared. These are both rational functions. The numerator is the constant polynomial 1, and the denominator for the reciprocal function is the first degree polynomial x, and for the reciprocal square function, the denominator is the second degree polynomial x squared. So although these are very simple polynomials, we do have the ratio of two polynomials, and therefore we can classify these as rational functions. Now you see the graphs shown there in the notes, and one of the things we see with rational functions very frequently is the occurrence of asymptotes, that is, lines towards which the graph gets closer and closer as x increases or as you get close to a particular value of x. So a common characteristic of the graphs of both of these functions is the existence of asymptotes. For both graphs, the y-axis, that is the line with the equation x equals 0, that's the y-axis, is a vertical asymptote, and the x-axis, which has equation y equals 0, is a horizontal asymptote. As I mentioned, asymptotes are commonly associated with the graphs of rational functions, although a rational function does not actually have to have any asymptotes, but we very frequently will encounter them when we're dealing with rational functions. There are actually three different types of asymptotes that we'll consider for rational functions. We've already mentioned horizontal and vertical asymptotes. The reciprocal and reciprocal square function each have one horizontal and one vertical asymptote. We'll deal with how to identify horizontal asymptotes later. For now, however, let's just note that the vertical asymptote for each function, which is the y-axis or the line x equals 0, is associated with a value of x at which the function is undefined. We see that the reciprocal function and the reciprocal square function are undefined at x equals 0. So when we're looking for vertical asymptotes, we're looking for values of x at which the function is undefined, where we get division by 0. So now we will state the rule for finding vertical asymptotes of a rational function. Given the rational function f of x equals n of x over d of x, if there exists a real number a such that d of a equals 0, but n of a is not equal to 0, that is, a value of x at which the denominator is 0, but the numerator is not simultaneously 0, then the line x equals a, and that is the equation of a vertical line, x equals a constant, is a vertical asymptote of the graph of f. In other words, any vertical asymptotes of a rational function are associated with the zeros of the polynomial in the denominator. So to find vertical asymptotes, we need to look for the zeros of the polynomial in the denominator. These are the values at which the rational function will be undefined, since these values will give us division by 0. Not every zero of the denominator may necessarily be associated with a vertical asymptote. But if there are vertical asymptotes, they are always associated with the zeros of the denominator. Let's turn now to example 1 and find some vertical asymptotes, if we can, for some rational functions. First example is f of x equals x plus 1 over x times x minus 1. Notice we have the denominator in factored form, so we'll take advantage of that. We want to focus on the denominator in finding vertical asymptotes. Basically set the denominator equal to 0 and solve for x. We would get x equals 0, x equals 1. And basically by solving for x here, you have identified the actual equations of the vertical asymptote, because the equation of a vertical asymptote just has the form x equals a constant. It's as simple as that. The only other thing we have to make sure of is that the numerator is not 0 at either of these values of x, and it's clear that it's not. 0 plus 1 is 1, 1 plus 1 is 2, so the numerator is not 0 at either of these values of x. Now x equals 0 could also be identified as the equation of the y-axis. So we could say the y-axis is a vertical asymptote, and the line x equals 1 is a vertical asymptote. Now I provided you with a separate sheet for the section 3.6 notes with the graphs of many of the examples that we'll be looking at in this set of notes. So I'm now referring to that sheet and just want to draw your attention to this first graph, and you can see what the graph looks like. This is the graph of example 1a, and you can see the y-axis and the line x equals 1 are vertical asymptotes. Notice that for x equals 1 we have a dashed line shown. So we indicate vertical asymptotes as dashed lines. We don't have to do that with the y-axis since the y-axis is already there. But you can see how the graph gets closer and closer to both the y-axis and to the line x equals 1 as the values of x approach either x equals 0 or x equals 1, again where the function is undefined. Now moving on to example 1b, g of x equals x squared over x squared minus 4. Here again we focus on the denominator, set the denominator x squared minus 4 equal to 0, and then solve for x. there's a couple of ways you can do this. One way is by factoring x minus 2 times x plus 2. It's a difference of squares. Set each factor to 0 and solve for x. X equals 2 or x equals negative 2. Since neither of these values of x will cause the numerator to simultaneously be 0, we can assume that these are the equations of two vertical asymptotes of the graph of G. Now moving over to our other sheet and referring to example 1 part B, the second graph shown, you see the graph of this function G, and you see that you have indeed the vertical asymptotes at x equals 2 and at x equals negative 2. I would just point out that this is an even function. You see the symmetry of the graph about the y-axis. So two vertical asymptotes again for this function, just as in our first example. Next, example 1c, h of x equals 2x squared over x squared plus 4. If we take the denominator here and set it equal to 0, what we should recognize, is that there's no real number solution to this equation. There is no real number x whose square is negative 4. Now we know that there are imaginary solutions to this equation, but when it comes to looking for vertical asymptotes of the graph of a rational function, we have to look for real number zeros of the denominator. So this function has no real number zeros of its denominator. So our conclusion has to be that there are no vertical asymptotes of its graph. So certainly not every rational function has vertical asymptotes. On your page, on your sheet with the graphs, the graph of example 1c is shown here. You can see that this graph does have an asymptote, but it's a horizontal asymptote. We'll talk about that later. But notice there are no vertical asymptotes. The function is defined for all real numbers. And so when that happens, we don't see the occurrence of any vertical asymptotes. Our final example is s of x equals x squared minus 4 over x minus 2. If we take the denominator here and set it equal to 0, we get x equals 2. However, 2 also causes the numerator to equal 0. And this is because the numerator and the denominator share a common factor. If that common factor is canceled, then the function has a simpler form. It doesn't even look like a rational function anymore. Again, this is assuming x is not equal to 2, that we can cancel the factors in this fashion. So because the only 0 of the denominator also causes the numerator to equal 0, again, this function has no vertical asymptote. The graph of the function in example 1D is shown right here. And notice what it is. It just looks like a straight line. It looks like the line given by y equals x plus 2. But notice that at x equals 2, where the function is undefined, there's a hole in the graph, a little pinprick of a hole, which indicates that the function is undefined there. However, there is no vertical asymptote associated with x equals 2.